Hello, welcome to our first week of our R statistics workshop. I hope you've enjoyed the R bootcamp to give you kind of a foundational knowledge to be able to move forward. I think statistics is one of the most widely used, one of the things R is most widely used for in research. In fact, it was basically developed for statistics to replace Excel and the IBM versions and all that stuff. So I think we're going to start off by kind of moving through statistics here and being able to apply R in ways that can expand your usage to your own research. And basically for our first week, we're going to kind of build upon what we've done in the past, and we're going to be doing kind of deeper, more comprehensive data exploration and descriptive statistics. And we're using cancer research data sets to make it a little bit more useful. So, today we're going to be examining like distributions of variability, how to do group categorical data statistics, and this is all going to really help build this exploratory toolkit that we'll be able to have like already built to be able to apply to our work in the future. So today we'll be, by the end of this session today, we'll be understand more to manipulate cancer-themed data sets. You'll be able to calculate and interpret descriptive statistics in a more comprehensive way that's relevant to cancer research. We'll try to understand some distributions that are found in biological data and be able to create publication quality visualizations of this statistical cancer data. So first, just kind of loading in just a slew of R libraries here. Most of these you should probably already have. Maybe ggmpubr you might have to add in, which is great for doing data visualizations. And today, we'll start out by kind of just introducing what you guys have already seen a lot of, basic cancer data structures, where you normally find things like clinical data, which like patient demographics, treatment information, molecular data, or like gene expression, mutations, and really outcome data or survival. So let me just show you how I created a comprehensive cancer patient data set for us to work with today. It's very useful to be able to you don't have to do it right now, but in your own data, sometimes it's useful to be able, I've talked before, to be able to make sample data to try out your functions and your analysis before you move on to bigger, real-time data. But anyway, so creating this cancer data set, just as simple. We'll create a data frame with a bunch of columns. We'll have our patient IDs, our demographics, age, sex, BMI, let's say, some clinical characteristics like tumor size, stage, grade, do you have lymph nodes, cancer positive in lymph nodes, treatment information, very important, what you've been treated by, and some common biomarkers you might see, like Ki67 expression for proliferation, tumor suppressor, D3 mutation, the ER status, positive or negative, super useful in things like breast cancer, right? And our survival, which is really great for doing our survival analysis later on, and just keeping the ages to a reasonable thing here. And if we kind of look at the structure of the data frame here, we have 200 patients and all of these different columns, which we see below here. We just took out the head, the first 10 patients, and you see kind of a overview of what data we will be working with today with our statistical analysis. So first, just kind of, I want to talk a little bit more about understanding the variable types. I know some of this is really obvious, but what you will find later on is a lot of your errors in your R functions will be because it has the wrong type. It'll be expecting a numeric vector, it's getting a character vector. So you're really going to need to really understand and always have an eye on what types of what types of data do you have in your data frames. And because remember, you can always change them. You can do, if you want to change to as.character, change to a character, you say as.character. If you want to change to a numeric, you just say as.numeric. It's very easy to change these over with, and you can just change columns at a time. It's very simple. But just to kind of look at this data set and look at the types in different categories, which you'll see, the thing that really jumps out are categorical and continuous. Those are the two variables you're going to work with most in our data sets in general. Continuous variables are basically just numbers. They can be any number, 26.2 or 26.3, as opposed to integers, which have to be 26, 27, 28, obviously. Then we also have our categorical values, which are just basically just names like are your sex, male, female, treatment, chemo, radiation, things like that. And then we have our ordinal values here, which are like ranked characters. They have a rank and a direction, like stage 1, 2, 3, grade 1, 2, 3. So I really want to be able to understand these, especially focus on the continuous and categorical variables today. And we can kind of look at our data set. We have pretty much even continuous and categorical variables, a couple ordinal, and that one integer variable. So first, let's just talk about missing data in clinical cancer research and how we can deal with that. So we're always going to have missing data in real life. I mean, one of your first things to do is to be able to understand and assess your missing data. So let's just give an example of how we might see this today. I'll show you how you could introduce some NA values. So basically, I'm just making a new data frame, taking our cancer patients data frame and calling it cancer patients missing, just for example here. I set a seed, so we would have to introduce the same distribution of NAs. If you want to redo this, and there's two different ways you can introduce NAs. I'm basically just calling different values in columns and replacing NAs, right? So I'm basically saying the missing indices are going to be 20 from 1 to 200, which is how many patients we have. I want to sample 20 out of this full data set. And if I look in here, cancer patients missing, Ki67 expression, remember this is a vector that I am subsetting this vector now by these 20 missing indexes, basically. So I'm just putting in a random sampling of 20, right? We could have put this all in one here and make it a little easier for BMI, and we'll just sample out 15 out of the 200 for the BMI column. So we're just introducing 15 BMI and 20 Ki67 NA values. And we can just kind of throw this in a table here. I'm basically just summing them up, summing the N is equals NA values in each column, and finding the percentages that we have now. We get up to, so we have 15 missing in BMI, 20 in Ki67, which is getting a little bit high. So 10% of all our values are missing. So that's worth keeping an eye on if you want to drop those or how if you want to replace those. There's all different ways of imputing we've talked about. The simplest being with the mean. We can kind of just visualize this really quick with the NANIR package. And it's just basically just a way of looking at NA value where we basically see our 20 and 15. It'll be if you had a lot more, you can imagine it would be a lot more fruitful to look at this. We could also look at how many actual rows have one or more missing NAs, because there could be overlap between those BMI and Ki67. So we can look in cancer patient missings, pipe that to filter, which is we're choosing the rows, if any, everything. So I'm filtering everything, every column that has an NA value. And I'm just calling this back and saying, what's the number of rows in this new object? And I can see 32, which jumps right out because we see this is 35 total, right? So that means that 3 rows do have overlap, have NA values for both of those. And if we look at the rows with NA here, we can see all of Ki67 NAs, and you can see here this patient 25, we have an NA and BMI and Ki67, so you see the overlap. So what do? Do we just drop these values? Do we replace them? I don't know, it's kind of hard to see in general in this data set right away, but just to show you what you can do here is you just basically take the data set, the data frame, and pipe it to drop NA, and that just automatically knocks out all the rows that have NA values. And if we look at, we've called this removed, if we look at the number of patients, there's 200 patients, 200 rows. If you look at the new removed one, there's 168, 32 are gone. If you remember, 32 is the number that had NA values. So we've shown that we've gotten rid of all these values. But what if we want to replace them instead? The Ki67 is 10% of our data. Do we really want to throw all of that out? Maybe we should just replace with the mean, for example. So let's make a new data frame called data frame Ki67 filled from the missing data set. And here we're going to look at replacing all the NA values with the mean of that column. So first, let's look at the mean. The mean is just the data frame, choosing the column Ki67 expression, and we're just getting the mean of it, right? NA removed equals true. We don't want to divide out the missing values, right? So just the mean of all the values that don't have NA, right? And then we're putting them in to where all the NA values are. So every NA value is going to be replaced with the mean. And we're doing this by here, we're just having our data frame and we're calling our column, right? Our column is just KI67 expression, and then we're subsetting. What are we subsetting for? All the NAs, right? Well, if a column says, if a column has is NA, so is there an NA in this column, then put the mean in. That's all we're doing, right? And then we're just basically, once again, filtering out all the rows that have that anything. A value, now we're seeing 15, which makes sense because there's 15 BMI. So all the KI67 have been replaced. And we can actually look at this here and see that 31.55 is seen several times. So the mean has replaced all these values, which is very useful. I've done this and seen results, good results in this in data sets. But like I said, there's all kinds of complicated ways to impute values or get rid of outliers. There's just a one simple way. The important thing is to know they're there, how to visualize them, how to find them, and then you can, that's easy. Once you have all that, then applying options to replace them is really not that hard. So now we've kind of looked at cancer data structures, explored basic data structures. Let's get into some more comprehensive descriptive statistics. And the first thing we can do is look at a measure of central tendency, which sounds more complicated than it is. We're just basically getting a view of the very, very first view, the snapshot of the variability, right? And so we basically just want to make a function here. Today we're going to always make functions, and I'll show you how to apply these. So we want to make a function. The function is going to do a lot of calculations, right? And then we want to apply that function to every single column that we're looking at, which is going to be continuous variables. So we're going to take the data set, have a function, and then apply that to each column, right? So let's just assume we made the function. We'll go in here in a second, right? Basically, what we want to do is make a function where we put in a data frame and we put in a vector of data frame columns, and then we look at, we're basically getting rid of, and we want to look at any NA values when we're doing this. So NA remove equals true. I could have put NA remove equals true for all of these, but I'm just putting NA.rm equals NA.rm because I've set a value up here already. So either way would have been fine, true or putting the NA.rm here. And I'm basically just taking X, the vector I'm doing. I'm saying, first of all, sanity check. Is this vector numeric? If it's not numeric, then I don't want anything to do with it. The whole thing breaks, right? So it's just a simple if statement. If is numeric, then do this. That's it. Don't look at that too much. So then we're just saying, do this, do these things, right? So see all these things, really simple. I want to sum values that aren't NA. Then I want to round the mean, and then round everything else, get the median, get the mode, standard deviation, min max, Q1, which is the first quantile, which is below 25%, Q3 below 75%, and the IQR is Q3 versus Q1, the interquartile range. And this just gives us a distribution of the data. All of this gives us a kind of distribution of the data. So now that we have our function, where we need to put in X, so what is X? The vectors, right? Well, we're only going to do this continuous variables. It's the only thing that makes sense to do it by. So we grab all our continuous variables, make a vector, character vector of that, right? And we just put our vector in, put our vector in the function. Well, how do we apply this function to every column, right? Well, here's what we kind of built up to from learning about functions in the R bootcamp to now actually seeing how you can apply them in the vectorization optimizations of R. So basically, sapply is the easiest way to apply a vector and get a vector back. You can also use tapply to get to do transformations, lapply to get your list back, apply only in a simple ways. But sapply, I think, is the most useful for just applying a function across columns. So what am I doing here? I'm just saying sapply, apply this function to all these things. That's it. And I have the function already, right? Calculate stat. So I have the function, it just takes in vectors, and for each value in the vector, it calculates all these things, right? So I'm just saying, hey, I'm going to apply this function to all the columns that are continuous variables, right? So cancer patients is our data frame, and we want to subset that data frame, right? Well, we're going to subset the data frame for each column here, age, BMI, for every variable, every character in continuous variables. So basically, age goes in here. This function is applied to the age column. That's it. So it's just applied 5 times, right, to each one of these variables. And then remember, if you're applying to a vector, you're getting a vector back, right? It's a column, right? But I don't want these to be up and down. They're really long and hard to see. So I'm just putting a T here to transpose it. So instead of age going down, instead of age being going down like that, age is going across now. That's all I've done. So I've just applied this function to all these columns and then just transposed it, right? And if I cable that, you see here, I got my 200 patients and all my descriptive statistics across for all of our different variables here, right? So it's a good lesson here about how to apply a function and just get a very general overview of our data. Let's go a little bit farther and understand the variability of the data, right? Because this is very crucial to identify heterogeneity and outliers and variance, things like that, right? So first, we're going to look just simply at the coefficient of variation. Ever since you're in high school, you learned this is a very simple way of looking at the standard deviation over the mean, and gives you this CV value. The higher the value, the more variability here. And you see here, like the IQR is very high for survival months. It's also really high for survival months here. So you can see that it's another measure of our variability, right? So once again, let's just make a simple function, right? The function is just x, takes in a vector. Once again, a really equals true. And then I basically just make a function. Say, put in vectors and then do this. So it's real simple. It's just stx divided by mean x. That's it, times 100, right? So I'm just taking in a vector, find the standard deviation divided by the mean. There's my function. We're done, right? Then we're just making a simple data frame. The variables are just the values we're putting in, the continuous variables. And then we're s-applying. Remember, s-apply that function, right, to the variables in those columns, right? So s-apply the mean function to each continuous variable in the cancer patient data set, right? S-apply the standard deviation to each of them. And finally, s-apply our function to each one of those variables. Call that CV%. We're just basically making looking at the data frame here, and you see how we've calculated basically these values and these CVs based on our function. Once again, remember, just s-apply your function to that, and see how we're getting vector columns now. That's why we transposed up here. And let's look at a really quick way how we find outliers. Now, there's all sorts of programs and packages to find outliers. The idea is just to find things that have a different statistical measure away from the centrality of your data. One really easy way to do this is looking at the IQR. If you're outside of IQR, like when you plot those box plots and Boolean plots, if they're outside of the IQR to a certain extent, 1.5 times the IQR on the top, and 1.5, subtract 1.5 times IQR on the bottom of the median, then you will find that those are considered outliers, right? So, and it's just a way of defining outliers. You can define them any way you want. But anyway, that's what we're doing in here. So we're making a function. We're saying Q1, the first quantile, is equal to just a simple quantile function, x 0.25, right? And then for Q3, x 0.75. So we're getting all the data, under 25% and 75% respectively, right? And then the IQR, interquartile range, you're just subtracting the two to get the values. And then finally, you're saying this is an outlier if x is less than, so below Q1 minus, so we're down to Q1 already, right? Minus, remember, the 1.5 times IQR. So 1.5 IQR below Q1, or the pipe, or x is on top, Q3 plus 1.5 times IQR. So it's the value above the Q3. So below, or really far below Q1, or really high above Q3. Either of those things happen because of this or value, or thing, then it's considered an outlier. and then just sum the outliers. Tell me how many there are, right? And let's make a data frame of our variables, and then just s-apply our function, identity outliers. Remember, s-apply our function to our values, right? And our values are the continuous variables that we see here, right? Which are just the columns of this data frame. So make our function, s-apply the function to what? All our columns that we've chosen, right? And we see we have our outliers are summed now. And that's great. So now we know how many outliers we have, but how do we identify where they actually are in the data? So you may want to go and just delete that outlier, right? So how do you actually find them in the data? Well, luckily the function already found them and just summed them after, right? So just get rid of the sum. And then we just are basically finding our outliers. And then once we have our outliers, we can just basically run, or basically just, what this does is it gives you kind of a column of outliers, and basically says true or false if it's true, if it's an outlier, false if not. So we want to go find all the true values and see what rows they're at. And this is just my kind of own way of doing it. There's many ways you could do this, but what I'm doing is I'm basically making a data frame here, right? As that data frame, I'm running our function, but just for one patient. So that's why we don't have the s-apply here. We just have one cancer patient. I just want age only. I'm not s-applying this time, right? So I'm just looking at age, I'm finding the age outlier, right? And then I'm basically just piping the age outliers. I'm adding the row back so you'll know the row name, and I'm just filtering by basically if it's true or not. So I'm just basically looking at the outliers, looking at the outlier column, the true-false column, putting the row numbers back in, and then filtering by where a value is true, basically. So when I run that back, I basically found one outlier at row 72 in the age. So we'll see here there's only one outlier for age. If we put in BMI, we would expect to have two different ones. But then we know the row numbers. We can go find the row numbers, delete them, or deal with them if we want to. So I think that's really important, because a lot of times you'll plot clusters of things and you'll see the outliers. You want to be able to find those outliers out and delete them or deal with them in some other fashion. So next, let's look at the distribution analysis. Now I looked at the variability. Now let's look at the distributions. We're still kind of trying to get the same idea of how variable, or what kind of distribution does this data represent. So the first thing you can do that's really simple and obvious is to check for its normality. How normal is this distribution? A normal distribution, if you remember, is just kind of a bell curve. You just have kind of up and down. It's symmetrical on both sides, and the more symmetrical it is, the more normal the distribution is. And a lot of times you need to know if things are normal or non-normal to know what kind of test, statistical test you need to apply. So first, let's just look at two different ways that we can test for normality. Before we looked at those QQ plots, and then as a way to visually test, but how could we more statistically test to get actual number and a p-value if it is normal or not? And one way to do that is doing the Shapiro. The Shapiro test is a way where it'll actually give you a value from 0 to 1. The higher the number to 1, the more normal, and it'll give you a p-value. And if you're greater than 0.05, then you're normal. If you're less than 0.05, then you're not. So let's apply this to our continuous variables. So I'm basically just making a data frame once again with our variables as the names, right? And then for the Shapiro, I'm once again s-applying, right? But I still have a very simple function. It's just one thing. Instead of making the function and then calling the function a name and putting it here, I'm just going to actually put the simple one function, which I can just do by function x and have my Shapiro.test to x value, which is our input vector, and then we want to get the statistic value, the answer out of the Shapiro test. When you do the Shapiro test, it basically gives you a p-value and a statistic. So we just want to call the statistic for just this actual answer. So we're basically just rounding, we're applying it. S-apply, so we're applying the function to each of the continuous variable columns in this data frame, right? And we're rounding to the fourth variable. And that'll give us all our Shapiro values here. Same thing with p-values. We're doing exactly the same thing, except we're calling the p-value out of this test. And that gives us our p-values. And then basically we're just saying if Shapiro test is greater than 0.05, the p-value is greater than 0.5, then yes, it is normal. If not, equals no. And basically what our answer is, if we cable it, you see how the Ki-67 expression is the one that's actually is, the p-value is very low. It's below 0.05, so it's not normal. So everything is normal except Ki-67. So let's look at the QQ plots too. And if you remember, it was we do the QQ norm for each variable and QQ line for each variable. And for this, it's kind of easy to just run a for loop here. You could also probably do the sapply and do a function, but I think it's just simple enough here. So basically, I'm just saying for variables and continuous variables. So we have our 5 continuous variables, age, BMI, etc. I'm just saying for variable and continuous variables, do these things, right? So cancer patients, subset out the variable, do QQ norm, subset out the variable, cancer patients, do QQ line. And back to back, and then just plot each one of them, right? So for each variable, you have 5 plots. You see our QQ plots here. You see they all look pretty good, except Ki-67 has really kind of fallen off. And there are some tails in some of these, but more or less they're pretty normal if you look along the line. But you can see this Ki-67 is really tailed off. That's what's broken its normality here. So that kind of makes sense too. And one more we can do this is like, so now that we know how normal it is, what is the skew? How does it lean? How symmetrical is this distribution? So to do this, we'll look at skewness and kurtosis, which are 2 ways of measuring this skew. And we're going to use the moments library to do this. And basically what you'll find is if the higher the kurtosis value, the more skewed it is, okay? And the skewness actually gives us also interpretation but it'll also give us a value if it's right or left skewed. So first you have your kurtosis, how skewed is it? And then you have our skewness, which way is it skewed, right? Kurtosis, the higher the value, the more skewed. The skewness, if the absolute value is less than 0.5, then you're good, you're symmetrical. If it's not, if the absolute value is not less than 0.5, which we see that the only one of these, it would be our Ki-67 expression, that's why you're going to get basically a skewed interpretation. Because I'm basically saying if it's not, then it's going to be skewed right or left. I'm saying if it's greater than 0. So the absolute value of this is over 0.5. So this breaks, right? So I have to go to here. I'm doing it if else, right? So I'm basically saying, is it greater than 0? No, it's negative. So then I don't take that, I take that, right? It's the else, left skewed. So now I know I have it's not symmetrical and it's left skewed. What left skewed means, it's skewed to the right, really. So you have a long tail on the left and the whole distribution top is more toward the right. And basically what's happened here is the mean is moved outside of the median, the mode, to the left. Because the left side of that tail, or I should say this way, the tail, the left side, has skewed the mean over to the left. But in reality, it's more skewed to the right. You know what I mean? And let's see. And we can actually see this here too. Let's see. If we do like a histogram, right? Let's make that cancer data set. So I'm going to pull my library. Where's that cancer data set? We're going to make that cancer data set, right? So we have our cancer data set, and then let's just do a histogram with our basic plot, right, of cancer patients. And then let's just subset just out the age, for example, and see what we get here. Age must be numeric. So for histogram, so that's no problem. Let's just look at, we just need to call the second variable, right? So we'll take out the second column. And we're going to do this. This is probably not going to work, actually. I should have called it out. Yeah, it must be numeric there. Let's see. It's weird because you're like, aren't they supposed to be numeric? Patients to it's weird. It's saying it's numeric, but when I try to call it, it says I should be numeric, right? Alright, I'm being silly here. Because, like, it is numeric and it's not calling it. That's weird. I'll have to come back to this. I forget exactly. I'm not sure why it is doing that because it should be numeric. Data frame. There we go. I don't know why it was calling it that way, but this is what happens when you live code a thing. I think it's because I'm calling it as a vector here. So then it's an numeric value, and when I'm calling it like that, it's for some reason it's thinking it's not numeric. But I think it's really saying it must be a numeric vector, right? And now I'm calling it as a vector. That's why we're seeing it there. Sorry about that. So you need to call as actually the variable, but it really should work. I'm not sure what's going on here. It's just a matter of using the base histogram probably. But anyway, so you see this is numeric. We got what we wanted. We got that, but let's look at KI67 and seeing what the problem might be there. Oh, now it's skewed here. Now you see this left skew, right? This left skew distribution is high on the right, and that's why we're looking at that there. All right, let's get back to where we're going. This is what happens when you live code. Nothing works out perfect. Remember to put in a vector value, and really, it should. I'm doing the same thing as it's doing here, so it's kind of weird that it's not calling it. But anyway, it's some trivial thing, and that's how R is. It can be a little problematic sometimes when you try to. Remember how I mentioned at the very beginning, like you need to know if it's a character vector or numeric vector. That's where you run into a lot of problems. But anyway, we fixed it, so we're good. We're good. So but now you kind of see how that distribution is skewed over there. And that's why we're getting the negative skewness over 0.5. So now we know that KI67 is a little bit skewed, and that'll be useful when we're applying our different things later. So now let's look at more of a categorical data analysis. So let's just look at the frequency. If you just want to group things, look at the frequency of them. One way to do that is to use just the table function. If you just table a vector column, let's see what happens when we just table a vector column. And then we'll call that right after that and see what we get. Here's what you see here. So if you table things, it basically just grabs the different things that are in that stage. So and stage has 1, 2, 3, 4. So you have 1, 2, 3, 4 different columns, and then it counts how many are in each one of them, right? So you're basically seeing the stage and the frequency here. And we're just taking that value and we're just turning it on its side to have a nice data frame here where the stage or just the name of the stage vector, and then the as.vector of stage tables. So the top here are the names, and then that's the vector of frequency. So we as.vector of the stage table gives us our frequency, and then we just did a percentage here where we just divided that by the sum of all of them, right? And got a percentage here. So we see like the majority are in stage 2 and 3, actually the most are in 1, 2, 3, with the most being in stage 2. But just a quick way to get, look at the categorical data instead of the continuous variables that we've been looking at. If you want to look at two things, You can table just 2 vectors. If you table 2 vectors, it just sticks them together basically. So we have our stage values, and then it counts up everything in the treatment. And then just like we would think. And then if we want to see the proportions, this gives us the frequency, right? So frequency of 1 vector is just the frequency count of just that. The frequency of 2 vectors is we get the frequency of every single one of them. And if we want to get the proportions, we take this cross tab and just do prop table. A prop table of it, margin 1 is just visually looking at it, and we times by 100, round to 2 variables, and we see here we have the proportions. Now we have all the proportions of each variable. So you can group by anything we want and find by any variables we want and find their proportions and the frequency of them, right? So that's really important to grab the category of variables and see how they're playing out. So now that we've kind of looked at the descriptive statistics, the continuous categorical variables, how can we plot these in a statistical manner to get some more knowledge out of the data? Well, first let's look at some histograms and density plots here. First we'll look at a density plot, and you look below here, we're basically doing a histogram and a density plot on top of each other, okay? So the first thing we want to do is set the canvas, right? So the canvas is ggplot, cancer patients, which is our data frame, and we're just aesthetics ASing. The x-axis is age. So histogram, we just want x, there's no y, right? Then we add geom histogram, and then we AAS this. If we left this blank and didn't AAS it, we would just get the counts here, the frequency for all the bends, right? Or if we just put y equals, frequency or whatever. But you wouldn't have to put anything because it defaults to frequency, right? But if you want something else, since we have 2 things, which do we want? Well, we want the red guy to be the y-axis. So that's why we put y equals density for this value, because histogram is setting the x and y axis, right? And then we're setting the bends and just the color of our histogram, and that makes our histogram with density being on the y-axis, right? And then we add in the actual GM density. With using GM density, we add in the density plot, the red line, and it already has its values here on the left axis, right? And so we get our density plot, and then if you want to look at the histograms by stage, now we want to do cancer patients, AX tumor size. So tumor size is on the bottom, right? And we're going to fill by stage. Fill by stage. So what's happening is all these histograms are exactly the same. Each one of these 4 histograms is the histogram of the tumor size. You just can't see it because just these stages are actually filled in by these colors. So these values still exist here, they're just white. So we're just basically making one histogram and then just filling it for those 4 different things, right? So there's 4 stages. So we're making the histogram, right, for this data frame, for X value, and then we're filling by the 4 stages. And then we're basically just facet wrapping by stage to get our 4 stages, right? We're facet wrapping with 2 columns, 1 column, 2 columns. Otherwise, it would just put 1, 2, 3, 4 straight down. So the facet wraps it around, makes it cleaner, and there we have our result there. So that's great, but what if we want to look at some box plots and violin plots of the data? So let's first look at the treatment versus survival. What is the survival like in each of our treatments, right? So to do that, we want to make a box plot, right? And we're going to do our canvas first, right? Cancer patients, our aesthetics. We want X equals a treatment, Y equals survival, right? And we want to fill by treatment. We want to fill by the x-axis. And then we add in our GM box plot to get our box plot, our GM jitter to get our points to jitter around and not be just on one line so we can actually see them. And then we have our alpha is our opacity. The width is how much the jitter goes left and right. On our box plot, once again, alpha is the how transparent it is. The outlier.shape equals NA. That means we don't want to see the outliers listed there, the ones that are past 1.5 of the IQR. We don't want to see these here. What we did add is kind of a fun stat summary. There are lots of different things you can add here. I'm just adding the function mean here. So I'm basically adding a point shaped like a diamond and I'm filling it red. So basically the mean is the red value, because we already have the median of the black line, right? So we're just adding a fun little diamond for the mean. But there's lots of different functions you can add using stat summary. So there we go. So now we have our different treatments versus survival. Obviously we need p-values, but here we're just kind of starting, we're building up to that, right? Then we want to look at our violin plot. Here we want to look at what is the Ki67 expression in mutant versus wild type? Because maybe we'd expect more proliferation with our mutant, right? Our tumor suppressor is knocked down, so we see more proliferation or whatever, right? So how we make this box plot? Well, x-axis is going to be p53, y value is going to be Ki67, and we're obviously going to fill by 53 status, right? So just like we thought, ggplot, the canvas, right? Cancer patients, aesthetics, AES, x-axis, p53 mutation, y-axis, Ki67 expression, and fill by the x-axis, right? Fill by the difference in these two. This time we do GM violin with a GM box plot 2 in the middle. You don't have to do that, that's optional. And then we got all of our values. We didn't do the outliers equals an A, that's why we see our outliers pointed out here. We also didn't jitter our values here. So by not jittering our values, we basically just left them out there. We didn't want to see them at all. And sometimes you want to see like a mess of values. Sometimes it's just cleaner to show the plot. You know what I mean? I think it's always best to show the values, but sometimes it looks cleaner depending on your venue and what you're trying to do. So now that we've done that, let's look at some scatter plots and correlations. So scatter plot's pretty simple here. Should have flipped these, but let's look at the relationship between age and tumor size, right? And make a linear regression to see if there's any difference. So you can already see here, the X value is going to be age, the Y value is going to be tumor size, but we want one more layer. So we're actually filling the dots by actually the stage too. So we have our tumor size by stage as well too. So how do we make that? So once again, we set up our AES, right? Our backdrop, ggplot cancer patients, AES X for the x-axis, Y is tumor size for the y-axis, and then we add in our points, GM point, AES color by stage, and then we add our GM smooth method equals LM for linear regression. This time we're showing the standard of error, we don't have to. And I'm adding one more thing here. It's a little bit fancy here, but I'm adding in the R squared value. We can also add the equation here as well too. This is basically just we want to add it in the equation, the R squared value, to see how good that line actually looks, right? So by doing that, there's our R squared value, and we're seeing our fit is actually really bad. There's not much of a difference here at all between these two. So that's how we do our scatter plot. How about correlation? So there's different ways of doing correlation matrix. So correlation is very important. People use it all the time. I guess the first thing to think about is the method you're using. If you want to use Pearson, that considers it being more of a normal distribution. Spearman is more of a nonlinear, and Kindle's more a nonlinear too, but it's good for like really small sample size and many ties, things like that. And we're using complete observations because that's basically saying the row has to be complete, no NA values. You cannot have NA values for doing correlations. So you have to fix those or just use the ones, just drop the rows. So there's three ways of doing this. One is using the core, COR. That gives you your R value, your Pearson R. If you do core.test, you also get the p-value. And I have another method that I'm going to show. It's going to be R core R, and it's a value, a cool method of getting it all at once. But the simplest way of doing this is just to do the correlation, COR, of all our continuous variables in our data set, and then basically just plot that using core plot. And now we see here, we have our diagonal, and then we have all of our correlations, our Pearson R values, negative and positive towards the tumor, seen here. But they're all really low. You know, you really want something up more to 1, so it's pretty unlikely these are even significant. We really would need to have our p-values to see what is actually happening here. But that's just a good way to get a good look and plot on it using just the COR to get the correlation. Let's take this a step farther. How can we do this all in one? Now you could do core tests, get the p-values, do some fancy stuff, put them together, do some adjustments, but let's try to do it all in one step using this HMISC package that I think is pretty cool for this. So for this package, once we load it up, we just choose our method, Pearson or Spearman, and then we run this R core R plot here, and basically we need a matrix here, so we transfer this into a matrix. Same thing, our continuous variable columns in our data set, and we just choose our method, type equals method up here, Pearson, we could have put Pearson here too. This gives us our correlation matrix, and I'm basically taking this correlation matrix and I'm pulling out, you basically get an R column and a P column. I'm basically just pulling this out here, doing some fancy maneuvering and building a table from this. And I'm also doing one more thing. I'm adjusting the p-values here using the Bonaferi method, which you can just do, basically put your p-values and you do p.adjust p-value, your method here. This is something we'll be talking about more next week, but just to kind of throw it in there as a tease. And I'm also doing the absolute value of all the R's just to see, I don't care one way or another, I just want the highest values, right? But the important thing is I've used this R core package, I've used this HMISC package with the R core function, and that has all my estimate and p-values, and I'm basically calculating these last two columns. So really, R core R is just giving you the same thing core.test gives you, just in a cleaner way of stacking it. And then once I put this all together, table it, you can see here, we've stacked it by the absolute R being on the top, so we're descending to the bottom here. So we have our top 5 here have the most difference. But when you look here, you can notice also the p-values, and just the p-values are all over 0.05, they're all high, so nothing is significant here, which makes sense because the correlations are so low. One thing you can do with this plot, I think is really easy. Once you have that core matrix from the package, you can just pull out your R column and your P column. I named them R values and P values here, and you can just plot them really easily with that core plot. So I have my R values, my Pearson R. I have P.mat, which is it's counting for the P values and seeing if the significance, and if they're not insignificant, it's basically putting this X here. I also could put a blank here, and there would be blanks but here you would see nothing, so it would be kind of useless. So I think if some were just blank, I've gotten rid of the diagonal as well too, so it was cleaner. I think if you just saw the ones that were non-blank, I think that's probably the best way to show this. But this kind of gives you another way of easily pulling out those R and P values. You could also pull these out of core.test. I think it's called estimate and p-value. So it goes either way you want to work with that. One final visualization I want to show, just a tease heat map. Later in the semester we'll spend classes on heat maps only. I love heat maps. I love clustering. So let's just kind of do a tease here. You can look at the cancer patients and select out your continuous columns. So I just have my continuous columns. I'm going to scale them, and then I'm going to make a data frame out of them. So basically all I'm really doing is selecting those columns and scaling them and putting them back in a data frame. Simple as that. And then I'm going to sample 50 out of those patients, and I'm going to make a heat map. So I'm just going to, heat map data is just scale data that I've taken 50 patients out of, and I've plotted those here with feet map, and I've done, I think feet map and complex heat map are your favorite two plotting functions, and complex heat map's my favorite, heat map's my second favorite, and so we need to just transpose the data set so we can have these as columns, these as rows. So I just basically transposed it, put it in there. I clustered rows and columns, and I took away the column names, and here's what we see here. You see we're kind of, these are so different, so we're going to see these obviously stick together, and we see a couple little clustering here that come together, like in this cluster here, this cluster, but really not seeing a lot, which makes sense because there wasn't much correlation or differences between them anyway, because it's not a real data set. I did my best to try to give you something that resemble data set, and it somewhat does, but some of the correlations aren't there. So that's why you're not seeing them here, but this is the way to do it. If they were there, they would pop out. You could also do a grouped bar plot if you want to group by a cancer stage and treat. Let's say you want to group by cancer stage, and then also within that stratify by the the treatment type. Well, then you could just group by stage treatment, right? And then summarize the count. That's it. So now we have our stage treatment, and then just counted the number of patients, right? This groups equals drops. Basically, it means that I group and then I ungroup, because sometimes you want an ungroup to go into a ggplot. Not always useful, but sometimes it's needed. So we're basically just putting stage treatment back in ggplot. We're setting X for the cancer stage, Y the count, which is number of patients, and we're filling by treatment to get our legend in our different colors. We're doing GM bar, stat equals identity. We could have also done GM column. And then we're just doing, scale fill brewer to this set to column, and we're able to see our each stage and treatment types within each stage for the patients. And finally, if you want to do more group statistics, more of a stratified analysis like we just saw, it's really simple. You just basically want to group whatever you want and then summarize in any way you want, right? So I want to group by stage. I grab my stages, and then I want to summarize a bunch of stuff that have values related to each stage, right? So I'm just grouping by stage, I'm summarizing, I want the count, I want the mean, blah, blah, and then I put it back into a column. Let's say I want to group by a p53 mutation. Very important, right? I want to view p53 wild type versus mutant, right? So I group by p53 mutation, right? And then I summarize, and then I have all my summaries for that, right? Let's say I want to group by treatment. Well, here we go, group by treatment. Data frame, pipe to group by treatment, summarize, all the stuff. So anything you want to look at, just group by that out of your data frame, and then summarize or do anything you want to get those values for those groups specifically. That's a very useful topic, I think. So we've kind of gone through everything. Let's just do a few practice exercises to kind of build up some repetition in what we've done. So first, let's calculate the mean survival time by stage. Sounds like a grouping to me, right? So let's group by stage, take the data frame, group by stage, and then summarize. And one of those things will be mean survival, which will be in our survival months actually to get our mean survival. So we group by stage, and then we do a number of patients, and we're basically doing mean survival and the standard error of the survival, adding them onto. It's one of those group by stage and get some information about it, right? So let's actually try to plot that. So now that we have our survival by stage plot, right? So let's try to plot that. So it's survival by stage, right? X is our stage, Y is our survival, fill by stage because it's the X value, right? GM bar, stat equals identity, or it could be GM column, same thing. And there's where we see it. We see our mean survival for each stage. And here we want to add on, if you want to add on an error bar, just to show you, GM error bar, you basically set the AES for the Y minimum and the Y maximum, which we've made mean survival minus standard error survival and mean survival plus standard error survival. So that's how we're getting our values for it. And then it's basically just putting in, we're basically adding in GM text later with this mean survival actual number here. And the v-adjust could move this up and down to fit, or this is exactly something that I would put in Illustrator and just move those myself. It's just not even worth trying to figure out these v-adjusts, right? Because they're not going to apply the same to all the values. And so this is exactly the kind of thing you don't want to spend a bunch of time on trying to fix an R when you could easily fix that in Illustrator. The point is we have our mean survival by cancer stage. In our second exercise, let's just do a correlation matrix of all our numerical values, right? So let's look at all our numerical values, which we're going to select them out here because they're going to be count too, not just the numeric. So we're going to select out all the columns we need, right? Select the columns, right? Piped data frame. We have all our columns now that are numerical variables, right? Then we have all of our numerical variables. Let's use the core to get our correlations, and then just kind of show this in a plot here. So now we have all our correlations. I want to know my 5 strongest correlations here between different values. Well, what I can do there is I can get rid of the diagonal here. So I'm basically just saying this diagonal and A value is a diagonal. We don't want to see that, right? And I'm making a new data frame, and I'm basically just saying, I'm basically tabling the matrix here. And then that's basically just giving me the var1, var2, and the correlation. So I table this matrix. It's basically giving me these values, and then I want to orientate them, right? So my names are going to be var1. I'm just basically tabling it, setting my names, and then I'm basically looking for non-NA values. So they're not diagonal, right? And I'm basically just ordering out those values. So we don't want NAs, and we want to look at the absolute value here of the correlation and order them in decreasing value. So I'm basically just tabling all these values, right? And then I am finding the correlations that the absolute value is the highest. So once again, it's tabling all these values. These are kind of showing the correlations. And this is giving you the actual, tumor size to survival. Tumor size to survival is 0.13. You're seeing it there, right? We're just getting the top ones. So that was our kind of a way of getting our top correlation values. Let's go back to the other way that I kind of liked, the other method, the core R method, right? And let's throw in our same data frame, same columns, the numerical variables, remember that we used up there, and do our same fancy thing here, and we'll basically get the entire table the way we want. It gives us our Pearson R estimate, our p-value, adjusted p-value, and absolute value R. And please just feel free to steal my code and use this. If you have any correlations you need to make, just make a vector of the different columns, throw them in this code, you'll get the answer, right? And to shoot the top 5, is already really easy because I've already chosen the absolute value of R and make it descending, right? So I could just choose the header of 5, right here, it would give us the answer, right? But just to kind of overdo it, if this wasn't already done, I can just go back and do, this is called absolute R of the estimate, right? So I'm finding the absolute value of this estimate, and I'm calling it, in core test, I'm ordering the absolute value of the core test estimate in decreasing values, right? So the absolute value of estimates, decreasing values. And then I looked at the head of that to grab the top 5. But I didn't need to do this. This didn't need to be done here because I'd already done it in this arrange descending there. So if I hadn't done that, I'd have to do this. But anyway, I think this is much cleaner to get a nice big table of everything that's going on, and you can easily choose the top correlated values. And let's say we want to plot that. So I have that final data frame of our 5 different values, right? And I've showed you how to use the core plot, which is definitely the best. But what if you just wanted to do it in ggplot for some reason? Well, here's how you would do it. Basically, we have our variable 1, variable 2, and our estimate, right? So we're basically choosing var1 for our x, var2 for our y, and we're filling by our estimate, which is our p-value, and our estimate is basically being shown in this correlation with a higher value being red, lower value being blue, and we're basically using the GM tile, and we're basically, the scale fill gradient is what I did here to make this, where I'm just saying low is blue, mid's white, high is red. These could be any colors you want, and the midpoint equals 0, and the limits are -1, 1. So you can change all these values any way you want to get a different manual scale for these values. But you're basically just getting, the correlations, and you're getting your R estimate. There's no p-values here once again, but just a way to plot this other than using ggplot itself, if you want to. I don't know why you would there. In our exercise 3, let's visualize the relationship between age and tumor size. This is going to be a quick just scatter plot. So we want to look at age versus tumor size, but we're going to add some more things. Let's look at the stage and the grade as well too when we plot this, right? So this is kind of just an enhancement of scatter plot, right? So we choose our data frame, cancer patients, and we choose the AES our aesthetics for our background, right? So age equals X, right? Y equals tumor size, and then plus GM point. But now we're going to color by stage and shape by grade. So our points are colored by stage and shaped by grade. So we get 2 more layers of information on top of that. It's pretty good, right? And then we're going to do GM smooth by our linear model to get our regression, and that's going to be our dashed line for everything. And then we're going to do another GM smooth by a linear model, but we're going to color the line this time by our stage. So each line has its own stage value. So you see like stage red goes down, stage 1 goes down, stage 3 goes up. So you see some differences here, right? And to look and see if we could also plot the R-squared values if we wanted to, and things like that. And we've done the scale color brewer to get some nice colors that look together, and we have a pretty good multi-layered scatter plot here showing this age versus tumor size relationship. And we can plot out kind of the results here, where if I look in the actual correlation estimate, I get the Pearson's R, and I look at the p-value is 0.7. So you can see here, I can look at different ones here. So basically looking at the looking up higher at the correlation. So I see what I did here. I'm sorry. I did a correlation here below using core.test between age and tumor size. So it's one more layer. So if you use core.test, you get an object with an estimate and a p-value column. So I pulled out that column for the estimate and got a really low value and a high p-value, which is just expected. And if you look at just a linear model alone, you can just say LM, tumor size by age, the data, and that gives you, if you do a summary of that, you can just get the estimates for all your linear model to see, your p-value obviously is not working there. In our final exercise, let's generate a summary of statistics grouped by a p53 mutation. So that sounds like a group by to me, right? So cancer patients, group by p53 mutation. And then what can we do? Everything we can think of based on those values, right? So now let's put in age, let's put in tumor size, let's put in Ki-67 expression, no, it's positive, and calculate a bunch of descriptive statistics from the age medium to biomarkers, standard deviation, to they have lymph nodes, to the survival outcome. And now that we have all this value, right, this entire P comprehensive, we're just going to transpose that and basically just name the columns, mutant and wild type, and we're going to remove the mutation row because it's obvious. We already have these guys, and we're able to cable this and get a nice summary of statistics of everything happening between mutant and wild type. So once again, it's that group by, stratify groups you want to combine, and then provide any analysis you want to all of them. And we can do kind of a visualization with this. Now that we have it, let's look at our cancer patients, and let's select out just p53 mutation, tumor size, Ki-67 expression, survival. Just these 4 things, right? We're going to do a pivot longer just to change that to a ggplot. You could use reshape here if you want. We're just getting to that ggplot friendly data frame. And then basically we're plotting out the data here, where the X value is going to be p53 status versus our values for whatever variables we or expression or size or whatever. You can see the values are different for each plot. And we basically stratified these mutant wild type just like above, but we're visualizing it now. So we're going to do X, Y for the values, and then fill by p53 mutation. The fill by will give you the different fills for mutant versus wild type. And then we're doing a GM box plot, and we're doing a facet wrap for each variable. Facet wrap for each variable, right? And so our variables will be Ki-67, survival, and tumor size. And you can see here we're actually naming the labeler, those 3 things, and then we're basically putting that back in as a variable, and that's where we're getting the different labels of the facet wrap. So it's basically just splitting out mutant by wild type, by the value, and it's facet wrapping in 3 plots in one column, in one row. by the variable, which we're defining as one of those three variables, right? So then we see, Ki67 is higher in mutant, P53 is lower in the mutant, things like that. It's knocked out or whatever, and that gives a bigger tumor size. Kind of makes sense, right? We don't really know the p-values right now, if there are significant, and there are some outliers we've seen and plotted there. So next lesson, we'll be doing t-test, but just to give you kind of a quick tease for that, I can do a t-test, t.test is the base R way of doing it, tumor size by p53 mutation in the data, and I got a 0.02 value. So it is significant here by tumor size p53 mutation. So it's saying the tumor size is significant. And if we look at Ki67 by 53 t-test, it is not significant. And that makes sense because they're kind of close. And survival, once again, is not significant either. And there'll be ways we can plot those back online, show our p-values. We'll be going more over that next week. Just kind of a little bit of tease of how to do that. And finally, I won't go over this too much. We've seen this kind of before, but remember there's this library called Table 1. And when we do all this descriptive statistics, there's a way to table it down in a much nicer way for publication quality. You've seen all these nice, clean layouts for publications. Here I'm just, I'm specifying variables I want to summarize and specifying which ones are categorical. And I'm basically using the data, I'm stratifying by mutation, and I'm summarizing all these variables by P53 mutation. And so everything's stratified, really nice. And you can see the differences between all these different things that we've calculated. All right. So key takeaways, I've been to look at a cancer data structure and understand how to work with clinical, molecular, and outcome data. Obviously, we do that all the time, but now we're seeing how to use R to clean this up and arrange them in better ways and apply functions for things like descriptive statistics, which could be things like the central tendency, the variability, the distribution shapes we've seen to look at the skewness, the symmetry toward normality, which gives us a foundation to apply further models further down the road. And we've kind of gone over more comprehensive and detailed ways of making the visualizations based on these statistical analysis, using anything from histograms, density plots, box plots, violin plots, scatter plots, and heat maps. All different kind of ways that are obviously used every day and looking at these kind of statistical distributions. And we also looked at to stratify and group things together. We saw that group by is very powerful to form different relationships that we can even use the table 1 to give a publication quality table in the end. So great. So next week we'll be kind of building upon these foundations to do hypothesis testing based on, we're doing t-tests for comparing groups. We'll test assumptions, more normality tests, equal variance. We'll look at how to apply these back, how to change the way we view the t-test depending on these assumptions. We'll look at non-parametric alternatives when needed, effect size calculations, power calculations, and some other stuff. So we'll check that out next week. I think it'll be really, really practical and useful for you guys. And for additional assignment, I made a little kind of small homework assignment with 4 questions. And feel free to look through it and try it on your own if you can. If you don't have time, look at the answers. I have all the answers for you. We're basically just doing some data exploration and summary and statistics where we create a breast cancer data set. I did it for you and do some basic, data exploration, descriptive statistics, and handle some missing data, just things we've already done, right? Do some data phys, right? And then do some of those correlations, test for normality, even make a little t-stats yourself or find the p-values for the correlations if you want to look at that stuff early on that we'll go for. And you'll also create a nice big summary where you group by chemotherapy versus non-chemotherapy. So this is all really useful practice information. Try to go through it your own if you have time. If you don't, feel free to look at my answers. No problem at all. That's super useful to do, trust me. And additional resources, things that where we can pull data from, TCGA, SEER, there's a million places, CBio portal, where we can actually get data to play with. If you don't want to make your pseudo data set, right? And then you have your R graphics cookbook, which I think is a really, really great thing to look at. It's really basically a free thing right here. And it just shows you how to do really your basic R, your all kind of plots that you want to do, and I would go to back to the R for data science book to look at how to do it in tidyverse in the advanced R, because that's the way you really want to do it. That's the way it is done. And this concludes our first week of our statistics workshop. Thanks for staying with me for this. We covered really the comprehensive data exploration and descriptive statistics. Next week, more t-tests like I talked about, and applying these and graphing them, actually applying those p-values to the plots or anything like that. I know you guys want to see that. So for this week, please check out the additional assignment, additional resources if you want more practice. And if that's it, then we've concluded for the day, and I will see you guys for the next lesson next week. Thank you.